So we have a shaft which is rotating at 200 RPM. We have disc A down at this end and disc B a distance of 0.8 meters away. The shaft is supported on two bearings, C and D. C is 0.2 meters from A and D is 0.6 meters from A. So our task is to add an extra disc E, a distance XE from A, work out the mass of E and the position that E needs to be placed so that we minimize and equalize the load on the bearings. So in other words, we're saying both bearings are going to experience load R, and that's going to be at some unknown angle alpha. Now we have some additional info. We know that A has a mass of 10 kilograms, and for simplicity I'm setting this at an angle of 0 degrees. We know B has a mass of 8 kilograms and is at a radial distance which is perpendicular to the radius of A. So I've set B at an angle of -90. The radial distances for both are 2.5 millimeters, and we've been told that E has a radial distance of 25 millimeters. We don't know the angle though. I've called that theta E. So next we set up our table of values. So I have M in kilograms, R in millimeters, X in meters, theta in degrees, and then MRX. And we need to remember that each value in this column I'm going to need to multiply by 10 to the -3. That's because the R values are in millimeters. And then MR, and again each of these values will be 10 to the -3. So you work those values out in the usual way, and above this line is just the three masses A, B and E. Now it's a little different for the two bearings. We know the force on each one is equal and equal to R, and then we can remember, well, if force is equal to mR omega squared, then that means mR is equal to F divided by omega squared. So for us, we can't put a mass or a value for R in for the bearings, but we can put in an mR value. But instead of F over omega squared, we're going to use R over omega squared because that's what I've lost the diagram, one sec. Okay, we labelled our reaction forces on the bearings as R. And again, the angle for those is alpha. So consequently, in the table, we put R over omega squared kind of halfway between the M and the R columns because these are MR values. X is equal to 0.2 and 0.6 for C and D respectively. The angle is the same for both, and that's all we need to do in terms of the table for the moment. So for now we'll forget about the bearings and we can just draw our MR triangle. So if you look back at the table, the value of MR for A is 25 at an angle of 0 degrees. The MR value for B is 20 at an angle of -90, so that's vertically down. And then, therefore, the MR value of 25 ME must be coming up here at this angle. In order to achieve balance, we have to close the vector triangle. So the next thing we can do is work out the angle at which the MR vector for mass E is going to act. Okay, so that's the angle theta E here. So a simple bit of trig, tan of theta E minus 90, which is this little bit in here, is equal to opposite over adjacent, and if you go through the maths, that gives you a value of theta E equal to 141.3 degrees. And then using Pythagoras, we can work out 25 ME, and if you do that, you get a value of 32. Okay, so now let's look at the MRX triangle. So we know, again, looking back at the table, for B, we have MRX of 16 going vertically down. Now, we don't know the exact value of MRX at the moment for mass E, but we know that it must lie along this line at an angle of 141.3 degrees, the angle we just worked out. So wherever we end up along this line, in order to close this vector triangle, we need a vector which comes from this line and joins up here. And that will be the combination of the two moments acting on the bearings. And we want to make those as small as possible. So in order to do that, what we're going to do is draw a line which is perpendicular to this dashed line, because that's going to be the shortest distance from the dashed line to the starting point of our vector journey. Okay, so this is going to be due to the bearings, and we'll come back to that in a second. And that tells me that this distance here must be equal to ME RE XE. But I can actually work that out with a bit of trig, and I can also work out this length with a bit of trig. But first of all, we need to think about what does this mean. Well, we know that the force on both of these bearings is equal to R. And we know that MR, because we worked it out earlier, is going to be R over omega squared. So MR being M little r here. Let me just show you the table again. Okay, so if you remember, for the bearings C and D, we had MR values the same for both, R over omega squared. So that means for C, for bearing C, the moment MRX is going to be 0.2 R over omega squared. And for bearing D, it's going to be 0.6 R over omega squared. And because both of these act at the same angle alpha, in terms of vectors, they're just going to be pointing in the same direction. So that means we can simply add these two together as a single vector, and that's going to give us 0.8 R over omega squared. So let's add that to our little diagram here. So this is going to be 0.8 R over omega squared. Okay, so now we're in a position to work some stuff out. So for example, we can work out using simple trigonometry, because we can work out this length here. So we can say, I'll start you off, but I won't do the whole thing. We can say, well, ME RE XE must be equal to 16. So this is a right angle here, so it's going to be 16 cos 141.3 minus 90. Okay, and then with that information, and if you look back at the table, you should be able to work out fairly easily what XE is. Okay, so this will lead to working out XE.